Good afternoon, everyone, and welcome to our tinyML UK session. I'm definitely excited to moderate this talk where Professor Alessio Lomuscio from Imperial College of London, we're going to talk about AI safety. The talk is about verification of ML-based AI system and its applicability in Edge ML. So before starting with the presentation, just a bit of housekeeping. Let's introduce our sponsors and strategic partners. Thanks to them, we have our free events. Those are ARM, DeepLight, Edge Impulse, EMSA, Waves, Latent AI, HotG, ImageMob, Maxi Integrator, which is now part of Analog Devices, Quixel, Qualcomm, Reality AI, Seed, SenseML, SynSense, and SynChan. Present the tinyML UK committee. The members who are currently organizing the tinyML events, which are Alessandro Granda, Director of Technology, Edge Impulse, Dominic Binks, VP Technology from Audio Analytic, myself, Gianmarco Iodice, Machine Learning Tech Lead for the Computer Library at ARM, and Neil Cooper, VP Marketing Audio Analytics. Of course, if you have any interesting topics or you have any questions, don't hesitate to contact us. I mean, we are more than happy to accept other contributions for the tinyML UK sessions. So this is about tinyML Asia, and this is just a reminder that when the tinyML Asia will be live in November between the 2nd and the 5th, 2021. So you can register today. The event is virtual, is free, and thanks to our sponsors. So don't hesitate to register using the QR code here or clicking on the link reported in this page. This is about the ML vision, which we have already accepted the works and the project, and it was a successful challenge driven by the tinyML Foundation in collaboration with Axta.io. So the winners will be announced today. And there is a prize of 6K value. So the winners will be reported in the web page. This is the next tinyML talk. It's going to be virtual. It's from Ravi. It's a senior staff engineer and manager at Qualcomm AI Research. So in this case, we recommend you to register for attending this presentation about the enabling ultra-low power, always-on computer vision at Qualcomm. The event is at 8 a.m. Pacific time, the 7th of October, so this Thursday. Alessio Lomuscio is a professor of safe artificial intelligence in the Department of Computing at Imperial College London, UK, where he leads the verification of autonomous systems lab. He serves as Deputy Director for the UK RI Doctoral Training Centre in Safe and Trusted Artificial Intelligence. He's a distinguished ACM member of a Fellow of the European Association of Artificial Intelligence and currently holds a Royal Academy of Engineering Chair in Emerging Technologies. And with this, I leave you, Alessio, to drive the presentation. Thanks a lot.
Gianmarco, thank you very much. Olga, thank you very much for everything. And thank you for the opportunity. It's good to meet you all. And the opportunity of sharing some of the work we've been doing in this topic over the past few years. And I'd like to share some of the work we've done, which is funded by DARPA in the US and also in the UK by the Royal Academy of Engineering and EPSRC. Now, I only have 40 minutes. This is what I'd love to be able to share with you. I'd like to tell you who we are and where we come from a little bit, and tell you why we'd like to verify ML before we deploy it, and share with you what we're verifying in ML. Ideally, I'd love to be able to show you entirely how we're verifying ML. We only have 40 minutes, and we've been working on this for quite a while. I'll just give you a glimpse of that. I'd like to share a little bit about which ML systems we've been verifying together with our partners, Boeing in the US. And I'm gonna leave this last. When is it the case you'll be able to verify EdgeML or tinyML applications? Okay, that's our plan. So we are on this path towards safe AI, or this is what we're working towards. And I share with you some of the difficulties with AI in high reliability systems. I think you'll be familiar with many of these. And again, I'll share some approaches we're developing to move forward on that. And I'll try to wrap up all of this in 40 minutes. Okay, so who are we? So we're at Imperial here in the UK, in London. We are passionate about AI, and we'd like to see AI in society, in the industry. And we also have a belief in robust computer science and robust engineering. Okay, so our work is really devoted to safety and correctness, so that these machines can be trustworthy in society. And I have to say, we're a little bit concerned about possible consequences of poorly engineered AI in society, and both in terms of the consequences that this may have, but also more broadly for adoption of the technology. Okay, so this is just to tell you a little bit about where we come from. 10 years ago, I would have been giving a talk such as this, right? So we were working on autonomous vehicles. This was a project that we had together with Southampton, and we had a great collaboration with them. And so we were tasked with trying to verify autonomous systems and show the reliability and, I guess the trustworthiness back then. People wouldn't use that word at the time, but crucially, the fault tolerance of that device. And sure enough, we were able to verify several missions, and we were encoding some modules as multiple agents communicating with one another. And we were able to verify systems before deployment, and also as I was saying, the fault tolerance of that system to potential faults. So we developed a whole bunch of methods to do that involved compiling, simulating state flow specifications into a formal engineering model that was analyzed, model checked, abstraction done on the fly, faults were being injected into the model, talking to engineers. We would then verify the consequences of that fault, going back to the design stage, sometimes automated synthesis for correcting automatically some of these faults, and trying to understand the design and really understand the envelopes upon which this machine could be left in the water on its own to go and map. Actually, was mapping the temperature and the salinity of the ocean. Okay, so that was a very complex piece of work and advancement of model checking technologies we were doing. And I have to say that, we were feeling pretty happy having achieved all of that. And now, of course, there was a big assumption that we were making at the time, and that was there was a great bunch of engineers and technicians that actually come up with the code for the whole of the machine, and that's what the machine was effectively doing underwater. And that's an incredible assumption that you now recognize is no longer valid in 2020. In fact, what's happening in 2020 is that increasingly autonomous systems and definitely edge devices are part of that, see models in which the agents are really neural symbolic. Okay, what do I mean by neural symbolic? Well, typically you have two aspects here that are cooperating and collaborating with one another. One aspect which is still symbolic or rule-based or traditionally programmed, but it's also paired up with another layer which is neural-based. Okay, so very often you have perception which is governed by a neural network of some sort, and it really is a paradigm shift, right? So, and the question is, what are the implications of this for autonomous systems and more generally for adoption? Well, I think we've begun to see some worrying consequences of this, and we've seen anybody in ML is aware of potential misclassifications, and increasingly we see in autonomous vehicles and autonomous systems in general the potential things that can actually go wrong with some unguarded application at times of classifiers. So why? What is different about ML? What is difficult about ML? Well, I think you're very well aware of all of this. We know that even on in-distribution data, we have some inherent fragilities in the behavior of the models. We have typically poor performance on out-of-distribution data. And more often, more worrying, we also have strong confidence sometimes on some classifications that are incorrect. And then there's a whole bunch of other features that many people talk about, such as lack of explanations, lack of auditability, and so on. All these things together make it hard, in my opinion, to validate AI before deployment. And so this causes an inherent risk of poor performance in several applications. And again, the risks are here either very severe risk in terms of safety and security, but also there is a real risk of non-adoption in much of the technology. Now, of course, there are some methods to try and address finding cornerstones that are now very well catered for by the models and so on. The typical tool that people use is adversarial search. Now, in adversarial search, you do not show correctness, right? So in adversarial search, you may be able to find counterexamples or adversarial examples, but if you do not find them, you cannot be reassured that the model is correct. So what I would conclude is that we really need to be thinking about methods based on verification, targeting ML system, along the lines of what we are very good at doing in hardware and in software. Okay, this is hardly the case that a piece of hardware now goes out without being extensively verified and validated. I would argue that we need to be thinking about doing the same for the ML applications that we intend to put out. So I see a lot of benefit in this, including increasing the safety, the security and trustworthiness of the devices, whatever they are. They make it auditable, and it also helps with accountability and fairness, which are all topics that there is a lot of attention to these days. Okay, let me move on to the what a little bit. What is it that we can actually verify if we're thinking about a neural system, right? So if you're coming from hardware, typically you may want to check for race conditions, or in software unallocated pointers and so on. What are we going to look at in terms of a neural network? Well, first thing I would say is that we could be thinking about local correctness with respect to a specification, which will be something like, I'm given an input, and I want to show that my model is probably correct on that specification for that particular input that I'm looking at. That will already be something interesting to be able to say. I think at the end of this journey, we'd like to be able to talk about global correctness. So given a whole input region we're interested in, we want to show that the model is correct for all those inputs, okay? But the question then becomes, what actually correct specifications do we want to look at? Okay, one of them is adversarial robustness. I think this is something that you're all familiar with. We know that CNNs or other even fully connected models are known to be susceptible to adversarial attacks. What are adversarial attacks? Well, these are slight perturbation of the image that we may not be able to detect, but actually cause a misclassification of the image. Okay, so folklore notion is that a classifier is robust whenever it assigns the same label to every pair of images that will not be able to distinguish. Okay, now this is not really precise notion. If we want to make it more precise, you'll be looking at norms of distances from an input, say X prime, and you'll be looking to, for example, an infinite norm or a ball around that input and say that actually all my input points around that point have the same classification. Okay, so what does this actually mean? Well, not only does it mean that nobody can maybe fool the model to a different classification, but it also means that your model, for example, if you're thinking about the sense of a camera or a device doing imaging, and you're thinking about some white noise that may appear on the sensor or purely some other perturbations, well, it means that actually the model is robust to particular perturbations you may have in the input, either caused by the lens or some noise that you have in the machinery. And generally speaking, you would agree that this is a good property to have. But more broadly, this is an instance of a general verification problem that we want to study. And that is, we simply have a set of inputs and a set of outputs. And what we want to be able to analyze is whether our model is correct with respect to this definition. Okay, so the local adversarial robustness is simply an instance of that, where we are taking this set of inputs, X, to be defined on an infinite norm, and Y to be the class label that we are interested in that for that particular classifier. Okay, so I'm expecting you to know about adversarial robustness, but I would like you to think more broadly than purely adversarial robustness, because this is what we do. We're thinking more broadly than that. So this input set may not just be this white noise perturbation, although that is very important. I'll be talking a lot about that for the rest of this talk. But think about this input set to be able to encode maybe geometric transformations. Okay, so maybe if this is a set, this is a phone. If I do a geometric transformation, I would still want this to be a phone. Okay, if this was a phone, this should still be a phone. If I rotate it, for example, I scale it up and down. If I change the color of this phone, it's no longer black, but I buy a red phone, it should still be a phone. It shouldn't be something else. Or changing the luminosity, the contrast, and so on. These are all functions intuitively that map different areas in my input set. And I would want to be able to reassure myself that my model is still correct with respect to those changes. Okay. I could also have, some re-illumination of my scene, and I may be able to operate in sunset or at dawn and still be able to detect cars and things like that. I may also have more difficult things such as occlusion, pose changing for my object, and so on. So in general, I'd like you to think of X and Y to be very complex objects that for which you want to show that and investigate whether your classifier is robust for. Okay, let me move on a little bit to the how. Now, I'm gonna be a little bit hand wavy here. There is a lot of maths involved. Please get in touch with us if you'd like to know more. But here's a couple of things I'd like to mention. So let's consider a deep neural network, and let's assume it's a ReLU network. I'm sure you're familiar with ReLU functions. So we take the max between 0 and, well, either the sum of the inputs or a weighted sum of the inputs and so on. And so we'd like to reason in terms of the possible outputs of this model. And here the difficulty is the activation functions. And typically we want to map this into a computationally feasible problem. Okay, I'll be talking about a couple of approaches here that we developed. We have more, but I want to give you two examples. One is a complete method for verifying ReLU-based neural networks. The other one is an abstraction-based method for verifying ReLU-based. One is precise, but maybe less powerful. The other one is not precise. It's another approximation, but it may be a little bit more powerful. Okay, so this work on mixed integer linear programming began at Imperial together with a student, Lali Maganti, who's now at Google in 2016, 2017, where we are able to associate the computation that's happening on a neural network to a mathematical object, which is a mixed integer linear program. Okay, so if you look at this function that you see here, these equalities that you see right in the bottom of the screen, you see that we are rewriting for a vector for the output of a particular layer, the ReLU function. And we also have this term, this m delta, which is governed by a binary variable delta. And what you should be able to observe here is that for the different values that delta can take, here delta is a binary variable, as I was saying, you actually have an equivalence to the original ReLU function. So the solutions to this for the binary variable delta equals 0 to delta equal 1 is exactly the ReLU function. Okay, so this means that actually, if I consider the mixed integer linear program, where I'm taking purely an objective function of 0, and I take the conjunction of all these expressions for all these constraints, linear constraints, for all the different layers, and I'm forcing the input to be the input of my model, and the output to be the output that I'm looking for, I can recast reachability and robustness as a mixed integer linear program. So you really have a theorem that says that the resulting program is feasible if and only if that's exactly the function that's being computed. Okay, so this means that immediately you can investigate the neural network, the ReLU-based ReLU network under analysis, which is a feed-forward in this case, through a MILP solver, such as Gurobi, for example. Okay, so this is very important. We are very excited about this. We started experimenting with this, and we found out we can verify models or a few hundred nodes. And the reason for this is that solving MILP is actually NP hard. So actually moving from a few hundred nodes, which we could do in 2017, to the hundreds of 1,000 that we can do right now is something that took us 3 years of work. So in the rest of the next 10 minutes, I'm gonna show just a couple of approaches that enable us to take this step of 3 orders of magnitude. But there is a lot more, not just by us, but actually by the whole community. Now, the first idea is dependency-based, okay? So solving MILP problems typically involves solving a branch and bound approach, and that's one of the fastest approaches. And so what we do here is that we relax all the integrality constraints into linear ones. We resolve the resulting linear program. If all the integrality constraints are satisfied, we terminate. Otherwise, we branch on the integral variable and repeat for each resulting subproblem. Now, of course, this is exponential in these binary variables, which ultimately are the neurons in your model. So the key insight here was to consider whether it is the case there's some dependency relation between the nodes. And so whenever a node is stable, it may be that some other nodes down the line somewhere else in the network may also be stable, either active or inactive. Well, if that's the case, there's no need to consider combinations that actually will never happen in these states of activity or inactivity of the different nodes. So this means that in our solution space, we don't actually need to compute all the possibilities and examine all the possibilities to find a solution. Okay, so in this particular slide, you see that if node 1, 2 becomes inactive, well, then node 2, 1, if you do the calculation for this ReLU, is going to be active. Okay, so in this picture here, I'm not going to examine the case where 1, 2 is inactive and 2, 1 is inactive. This is something that I actually prune from my search tree, and I can actually, and I can also, I can only consider the rest of the tree in terms of the computation. Okay. Turns out this is actually quite effective. So what we do is that we stop the branch and bound procedure at runtime. We compute the pre-activation bounds and compute the dependencies between nodes, either in the same layer or in consecutive layers. We express these dependencies as a further MILP constraint, and we add this constraint to the MILP problem being solved, speeding up quite a lot the resulting search. Okay. So moreover, in a paper that we presented only last month, we also use dependencies actually as a heuristic to speed up verification through simpler MILP formulation. And to do that, we actually identify the nodes that has a large number of dependent nodes, ideally the one that actually has the biggest number of dependent nodes. And we divide the verification problem into 2 subproblems that can be tackled in parallel, one in which this node is active, the other in which this node is inactive, because this enables us to simplify dramatically the resulting search. In terms of resulting tool, Venus is a tool that implements this technique, and a number of patents that actually gone into producing these techniques effectively works by pairing a dependency analyzer together with a MILP solver that interacts with the worker producing the verification results. There's a number of other things that Venus does that I will not cover here, including automatically splitting the input, automatically constructing a bound propagation, a gaming solution in case a solution can be computed more quickly. But effectively, I think this is a good picture for what Venus does. And it's something that's actually released as open source. I'll come back to these charts, but effectively we now are in a position to evaluate the performance of various techniques, and there's actually an annual competitions in terms of scalability and performance of the various tools, and Venus does very well against other MILP-based solvers. Now, MILP is a technique which is sound and complete, so every counterexample you find is a counterexample for the model. But here, I would like to tell you a little bit about an incomplete technique event very quickly. And this is a technique which is based on abstraction and relies on the following idea. So with MILP, before, if this was the computation that I had for my original input, I was maybe producing this exact image of the computation that I could actually derive. Now imagine that actually I have magically some sort of way of actually giving you an approximation, an over approximation of what can be computed, which is in this yellow line. And suppose actually my specification is simply asking whether the output is on the right-hand side of the 0 line for X, this green area here. Okay, even if you're not computing exactly here, you know that actually this is still good because this is still in the green part, so you're okay. Okay, even if you didn't really compute the exact map for that neural network. And this is what we do with this method on symbolic interval propagation and VeryNet. We have box constraints as input. We support a bunch of layers, fully connected, convolutional, and so on. We not only work with feed-forward, we also work with sigmoid and tanh. And so what VeryNet does, it computes an abstraction of the model and determines whether these abstractions meets the specification constraints that we have. Okay, so this is a good picture, I think, to show the capabilities. We are first relaxing these constraints and this model, and the relaxation involves the ReLU functions. We then have a verification phase in which we're searching for counterexamples, and it may be that we can determine that the network is robust or non-robust. If we cannot determine the result, we refine by branching on some of these nodes, making the abstraction a little bit finer to be able to determine the result. So there is a lot of maths behind this. Let me just give you one slide of what is the symbolic interval propagation. Effectively, we have symbolic expressions for the ReLU activations, both for the linear bounds and the upper bounds. And we are, by resolution, we are cascading these expressions through all the way to the output. And we come up with linear expressions that determine the lower bound and the upper bound. And what we're doing is that every single ReLU nodes could be linearly relaxed, both for the lower bound and the upper bound. Now, there is a lot of approaches in the literature in terms of trying to capture the tightest possible relaxations. If you're interested in that, just follow up on the papers. There is a lot of work actually in the literature, trying to find the tightest possible combinations of relaxations here. Again, if now a counterexample is found, the network does satisfy the specification. We are certain the network is robust. Otherwise, what we might have found is a spurious counterexample. Now, if you found a spurious counterexample, we actually trying to find a valid one on the real model rather than the abstract model. And most often than not, we can actually find a real counterexample. If you cannot decide because your area is intersecting with this yellow region that I showed before, well, we can actually refine automatically this abstraction and make it tighter and hope that we're actually able either to say that the network is not robust by producing a counterexample or show that the network is robust. Okay, let me now just jump over maybe a little bit on the graphs. VeryNet is a tool that recently participated in the NN Comp 21, I think that was a couple of months ago, and it really achieved state-of-the-art performance in many of the test sets that we have. And this table here is to give you a glimpse of what we can actually do these days. For CIFAR-10 models of 110,000 nodes, that's about 1 million tunable parameters of 6 layers, 6 convolutional layers with the noise input of this. This is something that can actually now be verified automatically by for example, by VeryNet and other tools as well. Okay, so I promised you to cover a little bit the which as well. So here I'd like to mention a little bit which models can we actually verify in practice. And this is work we've done between the group and Boeing in the US and Washington State, the group led by Dragos Marginentu. And so this is part of the work done with DARPA, funded by DARPA. So one use case we had was effectively a system that was estimating the cross-track error for a plane that was autonomously taxiing on a runaway. So you get it in, the snapshot of the runaway, and the out, you get the cross-track error. This is a model, 10,000 nodes. And so we wanted to assess the robustness against variable environment conditions. And in particular, we want to determine whether the cross-track error was always less than 1.5 meters under all the possible transformations. So we were considering also photometric transformation, noise, contrast, luminosity. We were checking for a few things here. Okay, so in some cases, we could verify the model was robust. In other cases, for example, this is a counterexample. We could find a counterexample where this is purely produced by a noise perturbation on the original model, on the original input, where actually the model here is saying 1.6 track error, where without noise actually was saying here 0 meters track error, okay? One point I'd like to mention is that Venus is complete. So in principle, all the counterexamples can be found with respect to a perturbation that's given as a task. Second case, we were, again, in a scenario where a plane is taxiing around, we wanted to be able to detect objects, and particularly detect novel objects with the smallest possible number of false alarms. And so given an image with the label vehicle, we wanted to check whether the model was robust with changes of that model with respect to 10 to the minus 4. And actually, by doing experiments, we found that actually the model was trained so well, actually was robust, at least with respect to the images we were checking. And so by increasing the noise, we're able actually to determine actually some sort of threshold where you will see some fragility in the model. And so we were able to find no examples of non-robustness when the perturbation was 10 to the minus 4. But actually, when we moved on to larger perturbation, 10 to the minus 2, effectively, we could find counterexamples for each of the image in the test set that we had. So this gives us an idea of where this fragility threshold is with respect to the particular classifier, particularly for the input, which actually gives you an idea in terms of how, you know, where you would expect some weakness from the system that you're using. Right, so if what I wanted to show here is that you can actually also find a counterexample. I'm not sure whether this is going to work. Yes, it does. So together with being able to give a proof of correctness, if the property is not satisfied, you're actually able to see the counterexample that's being produced by the tool for the particular property. Last case I'd like to mention, in case you're not working on imaging and maybe you're working on tabular data, this is something that may interest you. We had a decision maker for landing a go around where the input is sensory data purely, it's not images. So this is actually a tiny model that's taking as input particular parameters that include the velocity, the position of some objects, and so on as they are detected by other instruments. And again, we wanted to check whether there were variations of this input space in which the decision maker would flip from land to reject. And what we found by considering land and reject considerations is that land decisions are robust irrespectively of the epsilon that we are allowing for the changes, and reject decisions are actually less robust for increasing epsilon. And actually, if you think about it, this is exactly what you would want to achieve from a decision maker that does exactly this. So the land decisions are more conservative than the reject decisions. Okay. Now, in this, so far I've talked about infinite norms, so where we're changing all the possible parameters as input. But actually, in some cases, you want to do an analysis in which we're fixing some parameters and actually allowing other parameters to do. That's also something that you can do with Venus. So in one experiment, we were using a range for some particular inputs. In this case, it's the y coordinate of the vehicle, and keeping everything else fixed, or at least some other parameters fixed. So you can actually use different norms to analyze whether you can find counterexamples and so on. One thing that this enables you to do is actually to understand the susceptibility to misclassifications with respect to particular inputs, okay? So in this case, we were able to check that actually it's the velocity of the intruder that is the one that enables us to flip the classification more often. And again, if you think about it, this is actually meaningful because the velocity of the intruder in the decision of landing and reject possible intruder on the runaway is something that should make you flip your classification. Again, so this was a reassuring check for the engineers to be able to read. So let me just conclude here. So what can you actually do by running this analysis? Well, first, you can actually provide robustness guarantees, okay? In the sense that actually, if you get a guarantee that you don't have a counterexample, you have a proof for correctness, okay? Pretty much like a proof for correctness that you would have in hardware and software. You're pretty sure that actually in that region, your input space, your model is really, really good with respect to the query that you're asking, okay? In terms of scalability, nowadays we can do 1,000 nodes in seconds, even for large perturbations and for large high-dimensional inputs. And when we move to the 100K, then that's where we need to put in a lot more analysis. So it's something like a few hours on the desktop, or a lot less, obviously, on specialized machines. The point I'd like to make is that I've been talking about noise, but one can do a lot more than just analyzing noise in this space. Okay, so let me move on to the why. So I think verification here is really a method for validation and certification before deployment. I think it is in everybody's interest to identify the weaknesses of the model before deployment. And I think down the line, we will see methods such as this as part of a certification effort before deployment. It may also be that one day we will see regulations coming in, at least in some domains, such as safety critical system, where actually some compliance will be required with respect to VMV activities, of which verification is likely to be a big part of, in my opinion. If you're not particularly interested only in verification, I'd like to share with you that verification can also be a base for increased performance. And probably some of you have seen this already. So suppose that you have a way of generating a large number of counterexamples at runtime. You can see that actually, rather than using your standard augmentation methods for your data set, you could actually be using a verification-based approach for augmenting your data set, because these data sets are precisely the ones that are showing the fragility on your model. They're not generated a little bit randomly or through expertise that may or may not be applicable to a particular situation. You can actually build a training pipeline in which verification-based counterexamples are added at runtime until you get a measure of robustness you're confident with. Something else that we're doing is that we're actually patching a model automatically by using the counterexamples we find by minimally changing the model without impacting the classification, without impacting the accuracy. Okay, so I think in general, I think what I'm seeing is a general direction to move kind of the quality of the model for plain accuracy against the test set to multiple criteria that show the accuracy is still going to be very, very important, but also probably going to see measures of robustness, measures of reliability, and maybe one day measures of explainability as well. So here's the question of when. When can I do this? If I suppose I would like to be able to do that. Well, so let me share with you, the key parameters here are the model size, the input size, and what specification that you're looking at. So right now, I think the tech that we have can handle things like 100,000 ReLU nodes against non-trivial nodes. Larger models can be verified against less intensive perturbations. So it turns out the noise is actually pretty hard to do. Things like color changes are actually easier to do than pure noise. And some other perturbations are harder to verify. So, however, you are the expert here obviously in tinyML and edgeML. It seems to me by talking to a number of people in tinyML that actually the model sizes that you have, that you play with, and you're thinking about your applications are precisely within the range of things that can be tackled right now by the tech as it is. Okay, so if you're taking the present tech and think that, I have a classifier coming, being used right now on a Tesla autonomous car, can we use it? The answer may probably be, it probably is a little bit too heavy to be used in that space. For sensors, for edge computing, I think the technology could be in the position where actually these questions can be answered for the particular models that are being used. So there is a lot of ongoing work. I talked about abstraction. Clearly, linear relaxations are one way to do it. We're working on tighter relaxations based on SDP. Again, if you're interested in that, we presented a paper on this a couple of months ago at DeepSky. We're working on a number of transformations go beyond white noise. As I mentioned before, some transformations are very easy to verify, some are very hard to verify. Verification can be used as a building block for explainability, and semi-factuals and counterfactuals can be constructed on the basis of verification pipeline. Again, that's work in progress that we have. And in a completely separate, well, not completely, but in a kind of parallel line of work, we're working on closed loop neural symbolic systems, where actually the neural controller is part of a plant and several agents that are being controlled and are interacting and evolving like an autonomous system. Okay, I think I will wrap up now. I'm just going to pause for 2 seconds on this slide in case you'd like to follow up on any of the papers. But otherwise, I will wrap up with some key messages. I think that verification will be enabler for trust in AI, and accountability, fairness in all applications. And it seems to me that EdgeML and tinyML are in a great position to be able to take advantage of some of this technology. The benefits I see in verification include validation of the models before deployment, understanding, and actually higher performance given what we just said. We know that there is a lot of work that actually doesn't see deployment, but gets stopped at pilot study for all sorts of considerations, some valid. Very often we see work not progressing from pilot to deployment because of concerns on performance. Verification, I think, can have a role to play in increasing the number of transitions that we see into deployment. Okay, so it seems to me that the tech is interesting to be explored in the space of HML and tinyML. And what I will conclude with is that if you have comments, questions, problems that go beyond the Q&A that we're going to do now, just get in touch. We'd love to hear from you, your experiences and what can be done in this space. We work both in terms of academic collaborations through the lab at Imperial, the Verification Autonomous Systems Lab that we have at Imperial. And we're also involved in commercial activities through a spin-out of Imperial College called Safe Intelligence, and we'd be very interested in hearing from you. So get in touch for anything. I will stop here and take questions.
Great presentation, Alessio. I really enjoy it. I also have a question, but I'm going in order to what I have here on Zoom. So one question, I believe it was already answered during the presentation, but it's about scalability. So where do you think the practical bounds of your methods are? Would it scale up to a larger neural network like ResNet V2, for instance?
So this is a great question, Gianmarco. So what we found over the years is that the difficulty is not just the model size, but actually what the queries are looking like. So for tiny epsilons, there are some specifications for which we can tackle very large models, and there are even not too large models for which we struggle, even with if we have very large parameters to work with. So it really depends on a case-by-case basis. It is possible to verify very large models against noise for very small epsilons. And sometimes these very large models right now can only be verified against other perturbations, such as color changes or things like that. But in principle, it's a question of looking at a particular application and see what can be done for a particular application.
Perfect. Thanks, Alessio. So the other one is any project released as open source?
So
Yeah, go ahead. Sorry.
So the two tools that that you see in the slides are actually open source. They contain patented methods, which typically means that in a commercial environment, one would need a license to use. But VeryNet can be used freely for research purposes in academia and so on. In terms of the industry, I would say get in touch and we can have a discussion about this. Some of the tech that is in these tools is under patent from Imperial College. And in some cases, it's licensed, in other cases, it's not licensed. Yeah.
Okay. So the other question is, what are the programming languages and library used for neural network verification?
So much of what you've seen is actually built in Python, actually, and right now we may be building things in a kind of more efficient language. Right now, if you download the tools, you will find them in Python. Sometimes you need to rely on external software as well, such as an optimization solver very often. And so these are very often written in C.
Okay. So I do have a question, which is also maybe similar to one we have also on Zoom. So here we have talked about the validation of a model. So of course, it's going to depend. So the data set will have implications on the validation of the model. However, when we report the results, should we mention, for instance, the underlying algorithms used by the neural network model? I give an example because on edge devices, most of the times we don't use traditional convolution to deal with matrix multiplication, but with Vinegar, which basically return similar results, but not exactly the same because we are in a floating point domain. So when reporting this kind of results, should we mention, okay, we got these validation results using these underlying algorithms?
So the approach we're taking is that for any verification problem we're asking, we want to mimic exactly the hardware that you have. Okay, so if you're not using convolutions, you're using something else. We'd like to implement whatever you're using and encode that completely accurately before we put the verification queries. So there are some activation functions and some operations we support. I'm sure we don't support them all, but some main ones we do already, and these are programmed as accurately as we possibly can. For those that we do not yet support, I think we ought to look into whether they can be supported so that they can be used for whatever problem you're using that particular operation for. I think going down the path of doing an approximation and saying, well, this is nearly the same as that, I think that is possible, but one would need to quantify the error that you're introducing by doing this, a reasoning in terms of the error that you may be introducing in terms of verification toolbox, and be a little bit more careful. So my first point of call would be, I would try to implement exactly what you're doing on the hardware and try to answer that question as precisely as I can.
Okay. Thanks. The other question is, does the VeryNet map out the code main of the abstraction of the neural network in a theoretical working? Then compare this to what happens to input changes under specific noises.
So I'm not sure I completely understood the question, but in a nutshell, what VeryNet does is that it constructs an approximation of the model by linearly relaxing the expressions for ReLU nodes and computing the lower bound and the upper bound of these expressions and calculating the possible output and saying, well, look, it's going to be between this lower bound and this upper bound. And so in some cases, you're able to decide what you're doing in that space. Now, at the input level, you're going to have a set. So I think this is where the question is coming from. As long as you can define that set, you will be able to map at the output under that particular relaxation all the possible ranges that you may actually get. The tighter this approximation is, the more precise you're going to be at the output level in terms of where your output is going to lie. And therefore, the easier it will be for you to answer that particular verification query. So you like to be as precise as you possibly can, and being able to construct exactly or as close as possible the image that you have from the input over to the output, according to the function that you have, which is mapping the input set. Whether it's a color change, whether it's a noise perturbation, whether it's a geometric transform, whatever that is. Whoever is asking a question, please get in touch with me and we do a one-on-one. And I'm passionate about this thing, so happy to chat more.
Perfect. Thanks a lot, Alessio. Do we have any other questions? Wait just a few seconds to see if we have any more questions. Okay, actually there is one. Do you believe adversarial AI is the most important risk facing machine learning hardware deployments using computer vision or other ML detection methods? If so, how can these adversarial training methods be deployed to fix this problem?
So on the first question, it depends what you mean by adversarial attacks. If we really mean in a security context that somebody's going to come around and fool the detector by having cooked up an adversarial example, maybe yes, that's certainly a risk. Personally, I'm more concerned about things going wrong just because they go wrong, but actually there's nobody who deliberately hacked the system to make them go wrong. So in principle, I would say at least both. I think right now we are seeing a lot of potential problems. And if I'm typing in a picture of a cat and I get a dog, that's absolutely fine. I'm just gonna have a laugh. But if I'm seeing, if I'm seeing a pedestrian and I no longer see a pedestrian if it's dressed in yellow, then it's a big problem. Or equally, if you have a sensor for a room and a yellow fire is a fire, but a red fire is no longer a fire, I think that's an issue. So I think it's a major problem, and I think we need to tackle that. It could lead to not only safety risk or accidents, it could also lead to non-adoption. Now, adversarial training, I think, is very interesting, and I think we've seen a lot of movement in that space. Once we identify the parameters that a model is particularly fragile with, we can think about adversarial training. That is adding other components into the loss function and making the model resilient to those particular changes. I think that is very interesting. The question becomes, can we make the model as accurate as the previous model and add it to be robust as well? And I think we're beginning to see very encouraging signs in that direction. But one thing I will say is that I don't think we should see adversarial training purely against noise. I think in general, we should see adversarial training or training for robustness to be broader. And for example, training for potentially other potential changes that we may have in the input space, so that we are safe and secure with respect to possible changes to the input space, not just noise.
Thanks for the answer. So the other two questions, I think, that are going to be the last ones. The first, do we have similar methods for analog hardware AI?
Analog hardware AI?
Yeah.
I'm sorry, what do you mean exactly by analog hardware AI?
I believe in this case is using analog electronic systems to build AI or machine learning algorithms rather than digital circuits, I believe.
So right now, these methods are general in the sense that they can be applied to more than just purely the functions I've talked about. So if analog systems, for example, work on sigmoid and other activation functions, I think the present tools can already be applied to those. For example, Verinet already supports sigmoid and tanh. If it means other activation functions and more broadly in other patterns, I think we will have to look into that and understand what that would involve. I'm not sure.
And the last one, actually, do you believe that we are going to have so a trust AI in the near future? That we're going to trust AI?
That's a very good question. It's very hard to give an answer. I think we should try at the very least, and I think we should all do our very best to increase the performance. I think the risks of problems are very high. I think I mentioned that a few times already. I think we should do the best we can to make the AI that we can produce as safe, as trustworthy as we possibly can, and devote the necessary resources to give it our best shot, really. And then we will be able to assess whether it's secure and robust sufficiently for some applications. It certainly is going to be sufficiently robust and secure in some applications. And the question will be, how much performance do we want in some applications, or in other applications that may become a commercial decision. But I think it's, we owe it to everybody to make AI as safe, as secure as we possibly can.
Thanks a lot. Once again, we'd like to thank our sponsors and strategic partners. So as introduced at the beginning of this talk, are DeepLight, Edge Impulse, EMSA, Green Waves, Latent AI, HotG, ImageMob, Maxi Integrated, now part of Analog Devices, Quixo, Qualcomm, Reality AI, Seed, tinyML, SynSense, and SynCharm. So this slide is about ARM. One of the sponsors of tinyML. So ARM is building a machine learning story at different angles, hardware and software. Related to the tinyML space, we have a wide range of solutions, hardware, but also software like CMC where you can find the increased TensorFlow Lite full microcontroller. Okay, DeepLight. So in order to make AI smaller and power efficient, here in this slide we have reported also the link to know more about DeepLight. Edge Impulse, which offers an end-to-end machine learning from the dataset acquisition to the deployment on your edge and tiny devices, so such as Arduino or Raspberry Pi Pico, for instance. So thanks also to Edge Impulse. EMSA, so the AI for Internet of Things devices. So as reported here, they provide computer vision algorithms, IoT solutions for system on chip, and also sensing solutions. So also in this case, if you want to know more, we have a Q code reported in the website. Green Waves, so also Green Waves, so sensor, which provides sensor and hearable products to process rich data with energy efficiency. So if you want to know more, you can visit the website. HotG, so distributed infrastructure for tinyML applications. So also in this case, they provide deployments, automated deployments of machine learning solutions. So HotG is building the distributed infrastructure to pave the way for AI-enabled edge applications. Latent AI, so which is adaptive AI for intelligent edge. So you can visit the website also reported on this slide. Next. Okay, Maxi Integrated for enabling edge intelligence. So as reported here, we have advanced AI acceleration integrated circuit, low power Cortex M4 microcontrollers and sensors and signal conditioning. Quixo with AutoML. So this is for automating machine learning solution that builds tinyML for edge using sensor data. It is an end-to-end machine learning platform, as also described in this slide. Qualcomm AI research for advancing AI research to make AI ubiquitous and efficient. So here we have reported some of the key areas touched by Qualcomm AI research. So reality AI, for advanced sensing to your product with Edge AI and tinyML. So you can visit the website, reality.ai, for more information. SensiML to build smart IoT sensor devices from data. SensiML pioneered tinyML software tools that auto-generate AI code for the intelligent device. SynSense builds sensing and inference hardware for ultra-low power embedded mobile and edge device. Buys an end-to-end deep learning solutions for tinyML and Edge AI. Here we have also the website. Okay, and I think we have finished for today. I'd like to thank Professor Lomuscio for this great presentation. It was an honor to moderate this talk, and hopefully, I really hope to have another presentation from you in the near future. Why not? To discover more about this growing field in the.
Thank you very much, Marco. And thank you very much for the opportunity of showing some of our work. Yeah, thank you.
Thank you. And with this, have a nice evening, everyone. Bye-bye.